So it's the same with xenon tetrafluoride.
Yeah, I remember learning all of it.
Each of the bonds, the bonds are exactly the same, right? This is xenon atom. They've got the same polarity. I'm pulling this way, and he's pulling that way to the same degree, so there's no net effect. And the same here. So overall, there's no polarity. And the fact that there's lone pairs sitting on the xenon doesn't affect that, because they just sit there, right? They're not going to give any. And even if you want to think that the lone pairs are going to do something, in this case they wouldn't, because there's two of them. So it's a vector. The way to think about it is in terms of vector analysis.
But in 3D structure, it doesn't look like it's like in 3D structure. It would look a bit like the one we showed us.
Let's have a look. No, it's square planar. It's square planar. It's flat as a pancake.
Yeah, it's actually across.
Like one of the.
It's square planar, so it's like a square. Let's look at the geometry. There is the geometry. Well, I mean, basically what it looks like, if you look at this model here, right, this is sulfur hexafluoride. If we just imagine that those two guys are lone pairs, this is xenon tetrafluoride, xenon, fluorine, 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 fluorine. It's perfectly symmetrical. It's like a square with xenon in the middle.
I know at some point it'll be useful information.
And it's exactly the same. So it's perfectly symmetrical. Perfectly symmetrical. Right, other questions?
Yeah, you know when boron is not has the healthy deficiency and no one cares about him?
No one cares about it.
Yeah.
Well, you could sort of help him by giving him electrons.
Yeah, but well, basically my question was, when an atom has electron deficiency, does it become more electronegative than it's supposed to be?
No, electronegativity is actually sort of an intrinsic property of an atom which doesn't change.
Okay.
What does change is that it becomes more what we say electrophilic, meaning that it becomes more hungry for electrons. That's not really the same thing as electronegativity. So no, that's not. You can't really say that. But for example, you have systems like this. Even with carbon, you have them. These exist. They're called carbenes, and they've only got 6 electrons, and you can actually isolate some of them. But they're very reactive. They're very reactive, and exactly because the carbon is hungry for electrons, right? Hungry, electron hungry. We've got a special name for that because we call it electrophilic, right? Electro meaning hungry for, well, electrons. Philic meaning to like an electron. So it's electrophilic. And so if I offer this some electrons, like let's say OH minus, which has got lone pairs, it's going to attack it. And it's going to pick up those electrons because it's hungry for electrons. But it doesn't affect the electronegativity of carbon, it affects the electron hungriness of it, which kind of electronegativity is also, but that's an intrinsic property of an element.
So basically we have now, okay, we have to separate it because if I have like carbon mixed with oxygen, it basically has the 8 electrons, and so to speak, we have also a higher electronegativity of the molecule, but the single atom carbon is not more electronegative because we're still about the electronegativity, about the intrinsic way.
Yes, electronegativity is intrinsic for an element, but you can make an atom more or less electron hungry, electron deficient, by playing around with the substituents to which it is attached, yes. And that's what chemistry is all about, basically, is doing that to make things more or less reactive, right? So this is organic chemistry, but also inorganic chemistry.
I'll just have one real quick question that's not about chemistry anymore.
Yes.
You know, on our student portal,
Yes.
to look on our overall year program, like when our holidays, when our deadlines, etc., there isn't the MSP thing. Which one do we need to select? MSC? Well, because like there's a bunch of files for the different programs, and we need to choose which one is us, and there isn't the file that says Mastery Science Program.
Well, then
it's MSC.
Well, then it's MSC, because that's the old name of the program, so you can pick that one.
Okay, great.
All right.
Thank you.
One quick question I asked before, about the others. When we start to fill them in the exam, for example.
Okay.
Am I allowed to start with the 3D and then fill up the 4S?
No.
Because
No.
basically
The 4S gets filled up first.
that's the correct way. But if you start to fill them up to know like if it will react to something or is it like has like electron more or less, if you fill them up with the 3D first, that should be possible too, right?
Well,
because when you take electrons away, I imagine it like we have a fourth shell, even if you said that they are basically they're at the 3D shell too, but I still imagine the fourth one because we're talking about quantum levels.
Yeah.
So if I take electrons away, I take the fourth one away because it's the
Higher in
higher one.
Yeah.
So I could still count in this way too, right? Or
Um,
write it down in this way because that's the way I count. Like, actually.
well, give me an example. Because I'm confused.
I don't know, carbon.
Well, carbon doesn't have any S.
Yeah.
Let's write down the electron configuration of iron. Okay, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6.
If the 3D is full, it's not full up.
No, it's not filled up. You
That's
fill up
the
the
problem.
you fill up the 4s and then the 3d, right? Point is according to the principle of Aufbau. If I then want to take 2 electrons out, I take them out there.
Yeah, that basically is.
Now, what happens in reality is that but yeah, this is the correct way.
Right. And that's kind of what I was what I was like talking about earlier, like with this graphic. Like you've seen something like
Yes.
that? Yeah. So like that's what I said dip, I meant bump. It was an accident on my behalf because what I was taught when we were learning how to do those things is that when it comes to the transitional metals, that you kind of treat it like a speed bump. That whenever you're writing your things, so like when you come to the transitional metals, it does like a bump up to like 3D or whatever, and that's kind of how we would.
Oh yes, I see.
Yeah,
Yes,
I think I just explained it.
Yes,
for
well, I mean that's exactly kind of what's captured in that Aufbau diagram. It's the same
Yeah,
thing,
right.
just expressed
So,
differently.
if
I
we
found
talk
it easier
about
that way if you're at the table.
I have to go. So
Just if we talk about the molecular orbital theory, DMO theory, that's
Yeah.
how I love it actually.
where did you do?
Yeah, we did.
Where did you do?
In Dortmund. I'm not that good, but I know the stuff from there from the past 15 months.
Because
so.
because molecular orbital theory is quite sophisticated, right? I mean that's
Yeah.
I mean
If you go like in complicated way, but they didn't like because of the energy levels, they change, and so sort of you fill them up in the other way until some. I don't know what extent, but until some extent you can just fill them up easily, going the.
But molecular orbital theory is a whole different kettle of fish.
Yeah.
Molecular orbital
It's
theory is totally different. We didn't discuss it at all today.
Yeah, but still it takes the same topics like about energy level and filling up the orbitals. And there are differences if you get more complex. But if you start like with helium, like you have just the 2 orbitals left and right, and you fill them up completely, right? Yeah, exactly. For sigma bonding and so on.
Yeah.
If you start to fill up, I fill it always from down going
But that's
upward.
correct.
That's correct.
For a molecular orbital diagram, yes. But that's the same. It's the same principle as an Aufbau diagram. We start at the bottom and we go up. And the same principles apply in molecular orbital theory. You have Hund's rule and you have all this stuff. So it's exactly the same. The way you fill up a molecular orbital diagram is in principle no different from the way you fill up an
It
atom.
makes more sense to me why you're starting with 4S and then going to 3D. So that's why how I linked it. Just saying.
As long as you understand that, you know. I'm glad to hear that. I hope today's lecture wasn't too dense.
Yeah, it was dense, but I'm not some of it already.
Ja, if you did it.
I'm not sure. I'm not sure.
Als je Dortmund gemacht hast, dann